On the morning of February 15th, 2013, you woke up in Chelyabinsk, Russia, and went about your day. The sky was clear, cold, the way Siberian February is always cold, but clear. Nothing unusual. Traffic moved, schools opened, factories ran their morning shifts. At 9:20 in the morning, a fireball appeared in the sky. What happened next was recorded on more dashboard cameras, security cameras, and phone cameras than any similar event in history. Because Russia has an unusually high density of dashboard cameras, and because the event happened over a city of 1 million people during morning rush hour. The object was approximately 20 meters across. It entered the atmosphere at 19 kilometers per second. It had been traveling through space for approximately 4.5 billion years since the formation of the solar system. And in the final seconds of that journey, it compressed a column of air in front of it so rapidly that the air itself ignited. The explosion occurred at an altitude of 23 kilometers. The energy released was equivalent to approximately 30 Hiroshima bombs. The shockwave arrived at ground level 2 minutes and 40 seconds after the explosion, traveling at the speed of sound. It shattered windows across an area of 1,500 square kilometers. It blew doors off their frames. It collapsed part of a zinc factory roof. 1,491 people were injured, almost all of them by glass. They were injured by glass because they had gone to the windows to look at the bright light in the sky. The shockwave arrived while they were standing there, and here is the detail that changes everything about this story. No one saw it coming. Not the people in Chelyabinsk, not the Russian government, not NASA, not any space agency on Earth. The asteroid that injured 1,491 people and released 30 times the energy of the Hiroshima bomb was not on any tracking list. It was not in any catalog. It had never been observed before the morning it arrived. We found out about it when it hit. This is not an isolated failure. It is a systematic one. And understanding why requires understanding what we are actually looking for and how much of the sky we are not looking at on any given night. The current primary survey for near-Earth objects is called the Catalina Sky Survey, operated out of the University of Arizona. It uses a network of telescopes to scan the sky for moving objects, anything that shifts position against the background stars over the course of a night's observations. It is effective. It has discovered the majority of known near-Earth asteroids larger than 1 kilometer. Objects of that size, city killer to civilization ender, depending on the impact location, are now tracked with reasonable completeness. NASA estimates that approximately 95% of near-Earth asteroids larger than 1 kilometer have been identified. The Chelyabinsk object was 20 meters across. Objects between 10 and 50 meters, large enough to destroy a city, small enough to be nearly invisible to current survey technology, are estimated to number in the millions in near-Earth space. The current catalog contains a small fraction of them. The vast majority have never been observed. A 2018 report by the National Near-Earth Object Preparedness Strategy estimated that only about 1% of near-Earth objects smaller than 140 meters have been identified. 1%. The remaining 99% are moving through the inner solar system untracked, unnamed, and completely unknown to any database on Earth. And 140 meters is the threshold above which an impactor would cause regional devastation. Below 140 meters, the range that includes the Chelyabinsk object, we are essentially operating blind. Let's talk about why finding them is harder than it sounds. An asteroid in space does not glow. It reflects sunlight, the same way the moon reflects sunlight, but it reflects a small fraction of it, because most asteroids are dark. The average asteroid has an albedo, a reflectivity, of approximately 6%. Coal has an albedo of approximately 4%. You are trying to find a coal-black rock moving against a black background, reflecting 6% of the available light from a distance of hundreds of thousands to millions of kilometers. The Chelyabinsk asteroid was not found before impact for a specific additional reason. An approach from the direction of the sun. Optical telescopes cannot look toward the sun. The asteroid was in the one region of the sky that our surveys are structurally blind to: the daytime sky, the sunward direction, the approach vector from which a significant fraction of potential impactors will come. This is not a gap that better telescopes on the ground will close. It is a geometric limitation. You cannot point an optical telescope at the sun. Objects approaching from that direction will arrive undetected. The proposed solution is a space-based infrared telescope positioned at the L1 Lagrange point, a gravitationally stable position between Earth and the sun, looking outward into the region ground telescopes cannot see. NASA's proposed NEO Surveyor mission is designed to do exactly this. NEO Surveyor was approved in 2021. Its launch has been delayed multiple times due to budget constraints. As of current planning, it is scheduled to launch in 2027 at the earliest. Until it launches, the sunward blind spot remains. Now let's talk about what the data actually says about close approaches we did not know about until after they happened. In October 2019, an asteroid designated 2019 OK was discovered approximately 24 hours before its closest approach to Earth. It passed at a distance of approximately 70,000 kilometers, roughly 1/5 of the distance to the Moon. Its diameter was estimated at 57 to 130 meters. At the upper end of that estimate, an impact would have released energy equivalent to several hundred nuclear weapons. Not at a single point. An airburst at altitude, a shockwave across hundreds of kilometers depending on the angle of entry and the object's composition. 24 hours notice. At the upper size estimate, a potential regional catastrophe. In August 2020, an asteroid designated 2020 QG passed Earth at a distance of approximately 2,950 kilometers. This is closer than many satellites. It is closer than the International Space Station's orbital altitude at certain points in its orbit. 2,950 kilometers. It was discovered 6 hours after closest approach. We did not know it existed until it had already passed us. The object was approximately 3 to 6 meters across, too small to cause significant surface damage, but large enough to demonstrate the principle. An object of that size passed closer to Earth than many artificial satellites, and we found out about it when it was already gone. In 2021, an object designated 2021 UA1 passed Earth at approximately 3,000 kilometers. It was approximately 2 meters across. It was discovered after the fact. These are not anomalies. They are routine. The Center for Near-Earth Object Studies maintains a database of close approaches. The list of objects discovered after closest approach is long. It is updated regularly. It grows every year as survey capabilities improve, and the discovered after the fact column continues to accumulate entries. Let's talk about the one that matters most in this context. On April 13th, 2029, a Friday as it happens, an asteroid designated 99,942 Apophis will pass Earth at a distance of approximately 31,000 kilometers. 31,000 kilometers is closer than geostationary satellites. It is close enough that Apophis will be visible to the naked eye, a moving point of light crossing the sky over Europe, Africa, and Western Asia over the course of several hours. Apophis is approximately 370 meters across. When it was discovered in 2004, initial calculations suggested a 2.7% probability of impact in 2029. That probability was subsequently refined to 0 as more orbital data accumulated. The 2029 pass will not result in impact, but the 2029 pass will alter Apophis's orbit. The gravitational influence of Earth during the close approach will change the asteroid's trajectory. The new trajectory needs to be precisely calculated to determine whether any subsequent close approaches in 2036, in 2068, carry impact risk. The calculations currently suggest no impact risk in those subsequent passes. Currently. The precision of orbital mechanics at these distances and timescales means that small uncertainties compound. The 2029 pass will be the most precisely observed asteroid close approach in history, and the data it produces will refine our understanding of Apophis's future trajectory. A 370-meter impactor striking Earth would release energy equivalent to approximately 1,000 megatons of TNT. For context, the largest nuclear weapon ever detonated, the Soviet Tsar Bomba, was 50 megatons. Apophis would be 20 Tsar Bombas. An impact in ocean would produce tsunamis. An impact on land would devastate a region the size of a small country. An impact near a major population center would be the deadliest event in recorded human history by a factor of several hundred. Apophis is tracked. We know where it is. We know where it is going. The Chelyabinsk object was not tracked. We found out about it when the windows broke. Both of these facts are simultaneously true. Here is the part that the statistics make unavoidable. The Earth has been hit before. Not in human memory, in geological memory. The Chicxulub impactor, 66 million years ago, was approximately 10 to 15 kilometers across. It ended the Cretaceous period. It killed approximately 75% of all species on Earth, including all non-avian dinosaurs. The Tunguska event, 1908, Siberia. An object estimated at 50 to 80 meters across exploded in the atmosphere with a force of 10 to 15 megatons. It flattened approximately 2,000 square kilometers of forest. There were no human casualties because Siberia in 1908 was almost entirely uninhabited at that location. The same object over London in 1908 would have killed everyone in the city. The same object over any modern major metropolitan area today would kill millions within seconds of the shockwave arrival and tens of millions in the days following through infrastructure collapse, fire, and the cascading failures that follow the sudden removal of a city from a modern economy. We would have had no warning. The same blind spot that hid the Chelyabinsk asteroid hides a significant fraction of potential Tunguska-class impactors. The same survey incompleteness that means 99% of sub-140-meter objects are unknown means that a Tunguska repeat could be in an orbit that intersects Earth in the next decade, and we would not know it. The probability in any given year is low. The consequence, if it occurs, is not recoverable. You woke up in Chelyabinsk on the morning of February 15th, 2013, and went about your day. At 9:20, you went to the window to look at the bright light in the sky. You were still standing there when the shockwave arrived. 1,491 people were injured by glass that morning. Not because the impact was catastrophic, because it was small. Small enough that the shockwave only broke windows rather than collapsing buildings. Small enough that the object was in the untracked category, the 99%, the population of objects moving through the inner solar system that no catalog contains. The next one will also be untracked. Statistically, it has to be, because the tracked ones are the minority. The only question is how large it is when it arrives. NEO Surveyor is scheduled to launch in 2027, if the budget holds, if the schedule holds, if nothing delays it further. Until then, the sunward blind spot remains open. The catalog of sub-140-meter objects remains at 1% completion. The dashboard cameras in Chelyabinsk captured 20 meters and 30 Hiroshima bombs arriving without warning. The sky looks normal. It looked normal that morning, too. Your question. If a Tunguska-class object, 50 to 80 meters, 10 to 15 megatons, no warning, were confirmed to be on an impact trajectory with a major city in 72 hours, what do you think the realistic response would be? Not the movie response, the actual, logistical, governmental response to 72 hours notice of a regional catastrophe at an unknown until now location. Drop your answer in the comments. Next video, the objects that are not asteroids. The billion dark neutron stars moving through the galaxy that we cannot track, cannot detect, and cannot deflect. One passing close enough would not break windows. It would sterilize a hemisphere. See you there.